Assalamu alaikum, dear students. Today we are going to discuss the lecture number 2 of Geotechnical Engineering 1. Today the topic of our discussion is Introduction to Geotechnical Engineering, the origin of the subject, the mechanics, the laws, the various theorems which we will study in this subject, the application of this subject, etc. So those topics will be discussed in this lecture. First of all, we are going to discuss what is geotechnical engineering. The geotechnical engineering is basically application of civil engineering to earthen materials, that includes soil, rock and the groundwater. So commonly you have either soil in particular location, sometimes we have completely rocky formation, and sometimes we have mixed soil in which we have soil and rock both included in a particular location. Similarly, the groundwater is very important because it affects the settlement behavior, it affects the weight of the soil, it affects the shear strength of the soil. So we also discuss the groundwater when we are discussing the soil mechanics, whether it comes to rock or the soil. So we will also discuss some of the topics over here which will be related to groundwater in Geotechnical Engineering 1, like seepage and flow net, besides the basic soil properties which we will be discussing. So what is difference between soil and dirt? Usually we refer to soil as dirt, as khaura you call it, or matti generally what we say. So why we call it soil? So if you grow food in it, if you are get paid to analyze it like in engineers, or if you get a college credit for playing with it like you guys, then we will call it soil. Otherwise, for general people, it's just simple dirt. So when it is put to use, when it is analyzed, and when it is studied, so then we will call it soil. So for us as an engineer, as an engineering student, that will be soil. Now the branches of geotechnical engineering. Geotechnical engineering comprised of soil mechanics, rock mechanics, foundation engineering, geo-environmental engineering, geotechnical earthwork engineering and geologic engineering. So these are basically the main areas, the branches which are included in geotechnical engineering. Initially the subject was known as soil mechanics back in 1940s when Tarzai developed his pore water pressure coefficient A and B, and when he discovered the theory of effective stresses. Then civil engineers after that decided to treat the soil as a separate material because in the other geotech engineering materials like steel, concrete, we usually consider the total stress effect. In soil mechanics there are effective stress which are representative, which are usually responsible for long-term shear strength, which we will discuss later on in the subject. So that basically distinguished the soil from other materials like concrete or steel, etc. So there was need for different theorems for the soil. So that's why they started treating the soil as a different subject. Then rock mechanics. Obviously rocks are intact, cemented soil sometimes. Soil are just weathering from rocks. They are disintegrated pieces of rocks because of the various actions which we will discuss later on in the formation of the soil. So sometimes you have intact rocks as well. So rocks have different mechanics, they have different load bearing mechanism. So that's why we treat them separately and we usually study them in rock mechanics. Then foundation engineering is basically application of soil and rock mechanics to solve the foundation design related problems of large dams, structures, earthfill sites, deep excavations, tunnels, etc. So that will be discussed in foundation engineering. Then we have geoenvironmental engineering. This is recently relatively new field which we know of. Geoenvironmental is basically because we have nowadays contamination of the soil. That is very hot topic. We have been putting a lot of material in the soil, and generally we know that the soil can neutralize all the dirt, all the contamination, and the water passes through the soil, then it will be purified and you don't need to treat the groundwater, etc. So we know all these things. So we usually perceived soil as something which is a clean material, but recently, because of the increased human activity, now we have been putting a lot of the refuse into the soil, and lately the soil has not been able to deal with it because we have been putting too much contamination into it. So that's why that is also a very important subject area these days, geoenvironmental engineering, and we usually discuss the effect of various contaminations like chemicals, like human refuse, like plastics, etc., which we are putting in the ground and it effects on the properties of the soil. So we usually discuss that in geoenvironmental engineering. We have got MSc level course in our department on geoenvironmental. So when you are there, inshallah, we may be discussing this particular course. Then we have geotechnical earthquake engineering. So soil plays very important role in stability of any structure because the foundation is provided by the soil. No, in case of seismic condition, in case of seismic load, the soil obviously behaves differently, just like the other structures, because of the nature of the load in comparison to the static load. The seismic load is a small but repeated load. So that's why we study the effect and the behavior of the soil in geotechnical and earthquake engineering separately. Then you have geologic engineering, which is basically related to the basic soil properties, the soil formation, etc. Usually geologists they study them under the structural geology or engineering geology subject. So this is also part of the geotechnical engineering. Now, soil behavior. Concrete and steel, they are textbook material. They are manufactured material. Their properties are controlled. You mix concrete in certain proportion, you prepare steel in the plant, so they are textbook materials. Their properties can be controlled, they can be made to certain level of accuracy. While on the other hand, soil is basically a natural material. It is not manufactured, so it is basically formed by the natural processes. So its properties are usually not in your control and they are not usually known as well. So generally we commonly use term that every soil is different at a particular site. So no two soils are usually the same, although we try to draw correlations sometime, but they are less than perfect most of the time. So why is soil different? Firstly, soil is heterogeneous. Okay, what is heterogeneous? Heterogeneous is some material which has got different types, different sizes mixed together. Like you can see over here, this is a homogeneous material. All the particles are of same shape and same size. Okay, there are two things when we refer to the particle. One is the size, which you can see the extent, and then there is a shape. Shape is a 3D term, it's not a two-dimensional term. Shape means overall three-dimensional structure. Like this is, I can call it spheres. Okay, so they can be plates as well and they can be spheres as well. If they are platy, then it means that they will have circular section like this, but if you are looking from other angle, they will be like very thin, so then it will be plate. But if they are round like a ball, then it will be called sphere. So but in this from this direction they all look same. So anyways, coming back, this is homogeneous material and this is, you can see, heterogeneous material. All different shapes and sizes are basically mixed together, which you can see over here. The soil is same, so you can see some larger particles, some very small particles, some medium particles, then some larger particles. So unlike other materials, like if you see steel, it is more or less same when you look at it, but soil is heterogeneous. It is made of the particles of different shapes and sizes. Secondly, the soil is anisotropic. below you can see isotropic material. Isotropic material is the one whose properties are same in all directions. Okay, you can see over here, these are the spheres. If you apply load from this direction, if you look at from this direction and this direction, they look the same. Okay, but this is anisotropic material, which you can see over here. If you are treating this particle, this particular soil particle, in a vertical direction, it will be like a plate. Okay, but if you are treating it in this direction, this will be like a long column type structure. Okay, and we have different mechanics when you apply load from this direction in this direction. So this material will behave differently to the loading from different direction. So this is basically called anisotropy. Okay, so if the material response is same in our direction, its properties are same in our direction, then it is called isotropic material like this. But soil is anisotropic material. Okay, so that's why usually the other materials like steel, they are basically isotropic, which you can see like this. But soil is anisotropic material, so it's a different from other materials, and it should be treated as such. Then soil is non-conservative as well. Okay, it does not conserve its shape. Okay, it does not keep its shape. Like if you see, if you have a rubber ball and you apply load in this direction, it will become like this. But if you remove the load, it will come back to this direct. Okay, same as the other material particle like steel, etc. Their particles, if you apply load on them and if you remove it within the elastic range, they will retain their shape, they will come back to their shape. But in case of soil, when you apply load on it, if you take like for example this ball is a soil particle and you apply load on it in this direction, and then you remove the load, it will not come back like in this case. So it's a non-conservative material, it can permanently deform like other materials, so that's why it's different. And the same behavior is once again being discussed over here. Most of our engineering materials, we consider them and design them in their elastic range. You can see over here, elastic range means that stress strain curve is a straight line. Okay, so for the same amount of stress, there will be same amount of increase in a strain, so you can basically determine the slope of this curve. But in case of soil, it is basically non-linear. Okay, which basically means that when you apply load, initially there will be less deformation, but with the period of time, when you increase load, it will keep you giving more and more deformation for same load increment. Okay, so this is because of the elastoplastic deformation of the soil. Elastoplastic deformation is a deformation in which when you apply load on certain object, certain material, it will elastically and plastically deform. So when you remove the load, then the elastic deformation will be recovered, but the plastic deformation are permanent deformations and they will not be recovered. So that was discussion regarding why the soil mechanics is a different field, why we do not use the same theorems which we are using for steel and concrete for the soil as well, because we are applying the load on them, we are applying the loading on soil as well. So that is why the soil is different. Now coming to application of geotechnical engineering or the soil mechanics, various projects which we will discuss over here. One of the very famous historic and early application of soil mechanics was basically Panama Canal, which you can see in the following image. It is under construction. It's basically a canal which serves majority of the marine traffic, the ships. They basically use this route to reach USA and Canada. Okay, it is the shortest route available compared to the longest route from Pacific Ocean. So usually most of the ships, they basically use this canal, which is a man-made canal. Okay, so this was excavated back in early 20th century. So completion date in 1914. The total length of the canal is 47.8 miles. It costed about $375 million in 1914. So remember, it's a quite large, huge amount to be spent at that time. The capacity is to serve 14,000 vessels per year, or ships. The large ships are basically referred to as vessels, the cargo ships. The type is a lock canal, which basically means that they have got various gates which they close and open, and they raise the water level in various portions of the canal and lower it, because the one side of the canal is higher than the other one. Okay, so they have to raise the ships once they have entered the canal, so they close the gate behind it and they increase the water level, they pump the water inside the canal, so the ships goes up, and then they can move easily. The materials from which it has been cut are rock, clay, and structure is made of the concrete. Here is basically, you can see Atlantic Ocean on this side and Pacific Ocean on this side, so it is basically connecting Atlantic Ocean with the Pacific Ocean. In various locations you can see there are basically cuts through the land, so there are locks here as well, and then there is this huge lake which is Lake Gatun, and then over here you can see the cuts being made over here, and in the end it is connected to at the Gulf of Panama, it is connected to Pacific Ocean. Okay, so there are various locks over here, you can see over here, so there are central bridge. So in all this area they have to basically cut the whole area, like you can see over here. So they had to cut through mountains, and these are the barges you can see, which are basically making underwater excavation, and then they made these excavations through blasting and through cutting. So a lot of people lost their lives over here because they did not understand the soil properly at that time. The soil mechanics was not a separate subject in 1914. Remember that. After 1940 it becomes a separate subject as a civil engineering subject. So before that they did not understand the soil properties very well, so they were just excavating over here and they were getting all these landslides, etc. So they had a lot of challenges at that time. So the excavation, so the main problem they had was at Culebra Cut. The excavation of the cut was one of the greatest areas of uncertainties because they did not understand the soil mechanics very well. The slope stability and all these theorems, they were presented later on, okay, because when they understand the soil very well. So because they did not certainly understand it very well, so due to this, during the excavation there were unprecedented large landslides. Landslide is a large mass of the soil sliding down. You can see usually it happens in our roads as well, in the hilly areas, that the whole soils come from the top and it washes the houses down there as well and the road as well. So this is called landslide. So it resulted in large landslides. Americans who were building it at that time had lowered the summit of the cut from 59 meters, which is 193 feet, to 12 meters, which is which is basically 40 feet. So they made a cut of 150 feet, or almost equal to 15-story building. Okay, so during this time, and they were widening it as well, so they made the slopes of the sides very steeper. Okay, so for this they had to basically cut 100 million cubic yards of material to make that happen. But because of the landslides, they lost a lot of men as well, and a lot of people as well, a lot of equipment as well. And when they were excavating extra material, it was failing because they did not understand the slope stability, which is basically later on present in soil mechanics. So the material debris was falling, it was killing people, it was basically damaging the equipment as well. And it also resulted in a 30 million cubic yards of additional soil to be removed, which basically was because of the material coming by because of the landslides. Okay. Then another important project is basically Aswan Dam. I will discuss Aswan Dam over here as well. I can also discuss Tarbela Dam as well. Tarbela Dam is also embankment type dam made of the rock and clay, which is also earth-filled dam. So you can take example of Tarbela Dam as well, or you can take example of Aswan Dam as well. There are both large dams. Aswan Dam is basically, so you know much about Tarbela, so that's why I want to discuss about Aswan Dam. Aswan Dam is basically located in Egypt. In completion date is 1970. It costed $1 billion in 1970. and its capacity is basically 5.97 trillion cubic feet. The type of the dam is embankment. This is embankment, you can see over here. Okay, the raised structure which you basically make of soil, this is called embankment. Like Peshawar Islamabad motorway, you can see it is also made of embankment. Okay, you have filled a material and then on top of that you have constructed a road. So this structure is called embankment, and the material used for this embankment is basically rock and clay. You can see over here some rock over here. The clay is used inside, which I will show you in a while. Okay, so there was number of applications of soil mechanics in this dam, and any other rock fill dam you will have number of applications. For example, they diverted the flow first over here to a temporary canal being constructed over here through coffer dams. You can see upstream coffer dam, downstream coffer dam. So coffer dam is also embankment. It's a material which we bring and dump over here, so we can have a dry working area over here, because over here they wanted to build a dam from starting from here to here like this. So because of this they need to divert water, so they diverted over here and they created tunnels underneath over here, because they would be building the dam from here to here. So once the dam is complete, then after that they will just close this section and allow the water basically to pass through sluice gate of the completed dam over here. So there was a lot of soil mechanics application over here. So the another important application was basically the clay core. You can see over here. There is another problem in earth-filled dams, is because water can pass through the earth, through the soil, okay, very easily. So which will basically result into piping, erosion downstream. We will discuss all those phenomena in the later topics. So to cut this water path, so it should not go down this route in a very large quantity, we use clay, which is once again application of geotechnical engineering, because we know in geotechnical engineering that the clay has less permeability, so it does not allow the water to pass through its pores. Okay, so that is why also this is also application of geotechnical engineering. Not only we design this rocky material over here to sustain the load over here, but we also design this clay soil over here as well. So the knowledge comes basically from the geotechnical engineering. And then we have a grout curtain as well. You can see this is a grout curtain which they basically made. They are basically kind of a wall made of bentonite clay. Okay, they filled it with bentonite material, which is also a type of a clay. It's a soil, but it's got very less permeability. So they filled all this area. They just drilled the holes and filled it with this bentonite. So because bentonite have less permeability, it does not allow the water to pass through it. So that's why it was very, very helpful. Okay. The next project which I am going to discuss is basically the channel. Okay, or it is also called as Eurotunnel as well. It is also called, which is a fixed link between the France and the Britain. Okay, it's an underwater sea tunnel. I've also worked on the Ashford Kent section of Channel Tunnel when I was there back in England in 2005-2006. So the location is basically Folkestone, England, and Sangatte in France. Okay, so it basically one end is in England, another end is in France. The completion date is 1994. The total costed as $21 billion at that time. The length is 31 miles. It's basically a railway tunnel. So all the cars or passengers, they basically mount on the rail, and it basically transport them to the other side. The setting is underwater. It is placed underwater. Okay, they used a lot of innovation in this as well. Before that, they used to dig the tunnels by hand. You can see over here people are digging the tunnels, and then they have this access shaft over here. The bucket is being raised over here, and then they are removing the material from outside to the outside. So this was the old technique. During this, they discovered this new method of TBM. This is tunnel boring machine. You can see compared to the professors which are standing over here, you can see the size of the machine. Okay, so they just place this machine inside over here. They just make an access shaft, put a machine over here, and the machine then starts digging through these teeth which you can see over here, and the material which it is digging, it is basically sending it in the back. And at the same time, in this machine they have got tunnel lining capability as well. So they've got precast or cast in situ. Both methods are available, through which you can basically make the tunnel lining as well. So when this machine is just moving along its way, it is basically digging the tunnel as well with it. Okay. So this is also application of geotechnical engineering in the tunnels, which you can see over here. The other notable projects include the example of the San Francisco Bay Bridge in California, which you can see over here. It's a huge structure, cable stayed bridge. So there will be a lot of work needed over here to basically stabilize the foundation of these two piers, bridge piers, which you can see over here. Okay, so there was a lot of geotechnical engineering being in play for the foundation design. The total cost was 27 million in 1937. The length is 8,981 feet. Okay, and the type of the structure is suspension bridge. So the challenge over here was to build the foundation for the pier, which you can see over here for this pier. This is the foundation, and this is the structure which they basically made. So what they did, there is a type of a retaining wall which is basically called crib type retaining wall. We commonly use them nowadays as well. So this is just made of wood. So they make a cage of wood and then fill it with the aggregate, the heavy material. So it will basically keep the water out as well. At the same time, it will give stability over here, so you can make excavation. And on this side, they use sheet piles over here, you can see, which are made of steel. Sheet piles are being inserted over here. So they made this area for themselves. They reclaimed this area from water, so then they can excavate and they can place the foundation of the structure, which is on firm ground, and then they can erect their bridge pier, this one on this. Okay, so this is also a very important application of geotechnical engineering. Another application includes the tall buildings. Their foundations, they include some serious geotechnical engineering work nowadays, because their building load is very, very large. Like you can take example of Burj Khalifa as well. I can put Burj Khalifa over here as well, but you know much more about that, so that's why I talked about Petronas Tower in Malaysia. Okay, while in Burj Khalifa, the total length of the piles, if you combine them together, the pile foundation is like 5 kilometers. Okay, and they are very, very huge piles. So now coming back to Petronas Tower, it's located in Kuala Lumpur, Malaysia. Completion date in 1998. The total cost was $1.6 billion at that time. The height is 1,483. It is not the tallest building in the world, but it's got 88 stories. It's the tallest building in the Malaysia, at least. So its foundation basically included the pile mat foundation, which you can see there are a number of piles over here, and in the top we've got mat foundation or slab. Okay, so this slab basically combined these piles together and provides a foundation for the structure. You may have seen the same structure in BRT as well, when they made 8 piles, 9 piles in some areas 12 piles, and then they casted a slab on the top of that, and then on the top of that they basically were constructing their pier shaft. So same technique is being used over here. Okay, there was other geotechnical challenges in Petronas Tower as well, because the first site at which they were building it, at that site they had the sinkhole issues. Okay, there were carbonate rocks at that location, and you cannot build on carbonate rocks because they can dissolve with time in creating a void. We will discuss them later on, sinkholes, in the same chapter. So this was once again application of geotechnical engineering, which basically made it happen, which basically made it possible to construct such a large building at a particular location. So if they did not have the geotechnical engineering knowledge, they could not construct at that location. So there are various types of piles, like the piles which I show you over here. Once again, the piles are also a major subject in geotechnical engineering. You can see over here concrete pile being driven in the ground. So they've got this kind of cranes which basically lift it and then hammers these piles in the ground. So you can have these hammered piles as well. You can have offshore piles as well. You can see offshore platform. Okay, they are usually used for marine structures or for offshore drilling rig, which they use for petroleum exploration and pumping, etc. So they are also common. Other ground improvement includes the rammed aggregate piers as well. So what is that? And this, we basically at the location where the capacity of the soil is less. So what we do, we replace some of the soil with the good soil, with the better shear strength soil, with a better bearing capacity soil. So we use this auger bit, which you can see it's a 1.2 meter diameter auger bit, and we excavate the soil like this. Okay, so auger bit is excavated and removed the soil above. Okay, we just throw it to the side. So this is now the shaft being ready for heavy material. Okay, so we lower the cage over here. You can see the steel cage into it, and then we bring some granular material and we place it inside. Okay, so by this fashion, and then they compact it. So by this fashion we basically replace and create a lot of piles in the ground, okay, which are basically of greater capacity than the adjacent ground, because we have filled it with a heavy granular material, and then they can improve the capacity of soil. Here you can see after material is being put, it is basically tempered with the load. Okay, so we have taken a heavy load and we are basically compacting it. You can see over here is being compacted. Okay, so now they can they have this their cage, their steel being inserted over here. So on the top of that they will construct a slab. Okay, so they will connect the slab reinforcement with these steel bars, and then they will pour concrete on the top of it. Okay, the other ground improvement methods includes the dynamic compaction. Okay, we do compaction when our soil is not appropriate for the construction of particular structure. So sometimes it will happen that at a particular location, because you cannot change the location of the building, you usually have to construct on a particular site which is given to you. So that it is getting much and more demanding, because nowadays the engineer cannot change the site of the building. Okay, because that is the piece of land which the landowner has provided. So they can only do is basically make the soil better. Okay, by adding pier shaft, which aggregate filled piles, which you saw in the previous slide, or by compacting it with the load. If the soil is granular, you can see over here there is a granular soil, and this is a huge load which they have lifted from this crane. Okay, and they will drop it at these locations, which you can see over here, number of locations they will be dropping it, and because of the dropping of this load, the soil is being compacted and the crater is being created. You can see there's a crater over here, which is then filled with the extra material borrowed in. Okay, and then we will basically level it. You can see over here a bulldozer is being used to level the ground. So once you have completed this operation, then you will have a stronger soil compared to what you previously had, and you can easily build on it. The other important application of geotechnical engineering is landslides. Okay, you can see over here the tissue slide. This soil which you can see over here has been sliding from this location. This was like just like a mountain like this one before this one, and this is basically, you can see a landslide which has washed a lot of structures maybe on its way, etc. So usually they are catastrophic, the landslides. In the hilly areas you see them. They sometimes claim human life as well. Sometimes they basically claim infrastructure. So whenever we have slopes, whether they are natural or man-made, we usually make sure in geotechnical engineering they do not basically slide, they do not fail. Okay, so we design them in geotechnical engineering. This is, you can see a smaller slide, which you can see a small landslide. You may have seen it many times. Okay, so this is also part of geotechnical engineering. So to design a safe slope and stable slope. So slope stability we'll be discussing inshallah in geotechnical design, which is the third subject. Okay, here you can see the landslide claiming a lot of infrastructure. You can see because of the landslide from here, you can see the soil has basically been sliding in this direction and damaging all these houses. So the soil has come from here to here. Okay. Again, a landslide, they bring a lot of boulders and debris with them as well, which are usually dangerous. Okay, you can see over here a lot of mud being brought down by the landslide coming from the top. Then another important problem in soil, which I discussed earlier, you can see a sinkhole. Okay, this is what I was discussing about the carbonate rocks. In the area where you have erodible soils, the soils which can be eroded by the water, okay, easy by water flow, or if you have the rocks which can dissolve like carbonate, okay, carbonate is a whitish material you usually use for the whitewash tuna, so we usually refer to it. So the carbonates can dissolve under the ground, okay, and the only thin surface is left on the top, and if this carbonate dissolve too much underneath, it suddenly gives up and the whole soil basically collapses inside. You can see you cannot even see the bottom of this pit, okay, and you will be sleeping in your bed in the night and suddenly you will be inside this hole. It suddenly collapses, okay, so it's a very dangerous phenomena. Again, very important field in geotechnical engineering. Here you can see the close-up of the same, okay, and it suddenly happens. You can see the soil has been over here, the void has been created over the passage of time, okay. So it is also a very important field in geotechnical engineering. We detect these kind of soils, we detect these voids and then design accordingly, okay. Other applications like in geoenvironmental, I already talked about that basically relates to soil contamination. Whenever we build a structure, we don't want to contaminate the soil over here. So usually when you have refineries, in refineries we use a lot of chemicals, okay. So their foundation design not only include a safe foundation and design in terms of the loading, but in terms of chemical entering in the ground as well, because there will be a lot of chemicals being leaked in the refinery, being disposed of in the refinery. So if they are going through the floor, they will go into the groundwater, okay. So what we do, that we provide a clay cap, okay. So clay cap is a clay soil simply laid on the ground, because clay has less permeability. So if any chemical is coming into contact, it will not easily go down, it will not easily seep through this clay into the ground. So clay cap is being constructed over here. So clay is being brought and is being leveled over here, you can see, and then it is broken into pieces, which you can see, and then sheep foot roller is used to compact it, okay. So once it is being compacted, then after that we can actually construct building on it, okay. The refinery building or any chemical plant or any other plant which will have hazardous material should have clay cap, okay. So this clay soil will prevent the ingress, the entry of harmful substance in the ground from any leakage on the surface, okay. So this is also a very important application of geotechnical engineering. Here you can see a close-up of the clay, okay, being compacted by the sheep foot roller. Coming to earthquake hazards, also being analyzed in geotechnical engineering, because usually they are the phenomena arising from soil and rock. Here is the picture of San Andreas fault in USA, okay. You may have seen a movie on this as well, San Andreas. Recently, I think 2-3 years back it was released. This is one of the active major fault in USA, okay. So along this, because this fault is moving, so it creates a lot of seismic activity, okay. So this is also a part of geotechnical engineering to study that, not only the fault but effects which are induced by them. Here is basically Chichi Taiwan earthquake 1999. It damaged this particular dam. Over here you can see in the close-up, this failure was basically because of the earthquake, okay. So you need to design the building foundations to basically receive this earthquake. The earthquakes are also damaging for the buildings as well, because of the strong ground motion. The soil is moving in a one direction foundation and the building is moving in another direction. So that basically creates a lot of unbalanced forces on the foundations. You can see the foundation of the building being failed because of the earthquake in Turkey. Here you can see. Here you can see another important phenomena in granular soil, which is called liquefaction. If you have a granular soil like sand, and if it is fine sand and not compacted, and if it is fully saturated as well, and it is hit by an earthquake, by a seismic force, it can liquefy. So you can see the whole building has basically kind of sunk into its foundation. Okay, so liquefaction is also very important phenomena, and that we'll be discussing inshallah. Okay, here you can see because of liquefaction, the bridge foundations, they have given up. Okay, they have just settled into the liquefied foundation and given up. So also earthquake can induce the landslides as well. Here you can see the example of the landslide. You have also observed that in 2005 earthquake in Pakistan, there was a lot of landslides being triggered. So not majority of the building, they did not collapse because of the loads, but because of the landslides, the soil coming from above, the sides of the mountains and the slopes, they basically failed, they gave up, and a lot of soil was coming down and it washed away the houses on the way. Okay, so thank you very much for listening. This was just an introduction to geotechnical engineering, what type of areas are covered, why it is important to study geotechnical engineering, what are applications of geotechnical engineering. That is basically we discussed. Okay, so from next class we will discuss the geotechnical engineering for a historical perspective in the formation of soils, the various types of the soils and their deposition. Okay, so thank you very much for listening. See you next time.